Welcome to this Chemistry World webinar. I'm Ben Valsler, Chemistry World's digital editor, and I will be your guide through the platform that we're using today to help you make the most of the next hour. Now, saying that, today's webinar is unusual. There's no presentation, there's no software demonstration. We're not even baking cakes like we have done recently. Instead, we're going to spend an hour in the company of renowned chemist Melanie Sanford. Melanie is the Moses Gomberg Distinguished University Professor of Chemistry and Arthur F. Thurnau Professor of Chemistry at the University of Michigan in the US. She's won a number of awards, including the Blavatnik Award, a MacArthur Foundation Fellowship, and just last year she became the first woman to receive the prestigious Janssen Prize for Creativity in Organic Synthesis. Now, the full list of Melanie's awards is far too long for me to list right now, but I do recommend that you look at her institutional webpage to have a look and see quite how long that list of awards is. It's a real honour and pleasure for us to have her with us. The research currently undertaken in her group is varied, but themes include an aim to develop new chemical reactions that enable the production of pharmaceuticals, agrochemicals and fuels in a more efficient and environmentally friendly manner. Her work is used in academia and in industry. She's trained close to 100 graduate students and postdocs in her team, and we'll be very happy to talk about all of those today. So, Melanie, please could we get your camera and mic on and just check that we've got you with us? We have, I think. I can certainly see you. Can we hear you as well? Hello.
Yep, can you hear me?
We can. Super. Thank you so much for joining us today. I know you're incredibly busy, and we really appreciate the fact that you've spent so much time with us already getting this set up, and now we've got you all to ourselves for the next hour to do a sort of whistle-stop tour of your life and career so far. So if you have any questions for Melanie, get those into the questions box in GoToWebinar. I will get as many of those questions in as we can. But before that, we're just going to have a chat about your life, your career, your interests, your inspirations. And I think the best way to do that is to go right back to the very beginning, I think. Did you always know that you wanted to be a chemist?
So definitely not. When I was a kid, I'd really, my parents, no one in my family was a scientist at all. So for me, being a scientist of any kind really wasn't something I'd even thought about until I got to be in 11th grade. And I had a fantastic chemistry teacher for my AP chemistry class. So that was really the first time that I even considered the possibility that science was something that I was good at or could potentially do.
Do you think you had a leaning in that direction anyway? Did you have an analytical or problem-solving mind? Did you enjoy maths puzzles and building models or those sorts of things? Was there some indications early on that you might have a scientific mind?
Not really, I would say. I mean, I would, I think, you hear about a lot of these people that were sort of doing experiments in their garage when they were kids or, I guess, sort of being on math team and things like that. That wasn't really a big part of what I was doing when I was a kid. I was always good in school. I mean, I did fine in math. I did, but I would say that, my parents were both sort of more on the sort of humanities side of things. And I think that originally that's sort of what I thought that I wanted to do. And I was actually really good at writing. And so, which actually turns out to be a skill that's very useful in chemistry as well. But I think that was more the direction that I like to write. I like to sort of, I guess maybe my analytical mind was more in terms of sort of thinking about how to write things in an organized way, but never really any science until 11th grade. So.
And that was a chemistry teacher specifically, not a sort of general science teacher.
Yeah, so that was an AP chemistry class. Many people in the United States, will take this class, and I mean, I think this is something that I see even with my son now, who's in 11th grade, is like, it makes such a difference. Your teachers make such a difference, right? Having one good teacher in one class can make the difference about whether that subject is something that you end up pursuing for your whole life, right? And this is a really good example of that. And I think, this is one, I was telling some students this the other day, this is a teacher that actually, I never had a chance once I became a chemist, I became a successful chemist he was older. And so by the time I became a successful chemist, he had passed away. And so never actually had a chance to go back and talk with him and thank him for the impact that he had on my life. So I was telling some prospective students at a recruiting weekend a couple weeks ago, like, if you have a mentor that had an impact on you, you should tell them that, while they're still around, because I that's one of the things I regret is not telling him how much of an impact he had on me. So, yeah.
So a good teacher and clearly some established skills already got you into chemistry. And was it chemistry and nothing else from that moment on, or were you tempted by the other sciences? Could you have gone on a totally different path and become a world-renowned geologist?
I think that for me, so I think that what appealed to me about chemistry specifically, was first the periodic table. Like, I still think the periodic table is like the most amazing thing, right? Just sort of how it's organized and how it was figured out. And I don't know, I guess for me, that sort of organizing principle was always just it drew me in, and then I think when we were doing experiments, right, even in that sort of AP chemistry class, that we would burn the different metals and see the different colors, or doing a experiment on sort of freezing point depression and the idea that water freezes at 0 degrees, but then you can add salt and change the freezing point. I think that sort of physical like the physical manifestations that you could see of it and the sort of beautiful colors, that was what really drew me in. And so for me, and I mean, I guess, as we keep talking, you'll sort of see this, like, I would say that it was never like I was never driven by some big problem that I wanted to solve, like that I want to cure cancer, or that I want to, understand, how rocks formed or something like that. It was always just sort of, some observation that just got me interested in some, often very sort of technical thing. But then, yeah, I mean, what you can see from lots of things that you do in basic science is that then it starts to have broader implications as you kind of walk out from there. But yeah, physics, actually, I did very poorly in my college physics classes. Physics was not intuitive for me. And biology, I just found it to be a little bit too sort of observational. Like, I wanted something, I wanted to know more for biology, but then physics, it was too much knowing, So I think chemistry was the right balance for me.
I guess one of the advantages with the sorts of experiments you do in chemistry is the amount of input that you have. You can choose how much salt to put in and measure how much difference that makes to the freezing point and so on. Whereas with biology, it's frowned upon if you go interfering too much with the species that you're observing, for example.
No, that's a good point. Yeah. And I think, that sort of, I think that maybe another way to say it is that, like, the thing about chemistry is that at least organic chemistry, is the experiments are easy to do. Right. I think that for me, the idea that you would have to like plan for months and grow, cells and, in order to design one experiment that you're going to do, like, I like to be able to go in the lab and do something and see the outcome right away, and so I think that's what drew me specifically to sort of organic and organometallic chemistry as well, is that the experiments, you can go in the lab today and you can do a reaction and see the outcome of that reaction really quickly. And I think that for me, that sort of very rapid feedback was also really, really good. Yeah. So.
You talked about the colours of the flame test and so on. Of course, fireworks and the sort of on-stage whiz-bang chemistry demonstrations are often cited alongside things like having a chemistry set at home and so on as being the things that get people into chemistry in the first place. It sounds like sort of watching it on stage may not have been enough of an inspiration for you. It had to be something where you got hands-on and got involved.
Yeah, I don't think I'd actually, until I was in my chemistry lab in 11th grade, really thought about anything being chemistry or not, right? So I might see fireworks and I thought they were cool, but I didn't make that connection until I actually did it myself. So I think that's exactly right, and I think that then sort of, makes you think about how to draw more people into the field, right? Like how to make people, that they're just, you have to make that connection because everything is chemistry, and yet most people don't know that everything is chemistry, right? And yeah, so
once you'd had that sort of the life-changing realization that chemistry was the thing that drove you forward, what was your next step? How did you choose a university? How did you choose a course that you wanted to do at college? How did we move on from there?
I mean, I would say, my high school chemistry class, I thought it was cool. I'm not sure that I made the life-changing realization that I wanted to pursue a career in chemistry at that point. I think frankly, I chose a college because I wanted to do gymnastics in college, and so I needed to find a university. There's relatively few U.S. universities that have women's gymnastics programs, especially back in 1992, and especially women's gymnastics programs that would be the right fit for my skill level. So that was sort of honestly a big part of I was a good student, so I wanted to go to like a good university that had the right sort of level of gymnastics. So that was where my choices, it wasn't dictated by academics or chemistry necessarily. And then, I would say that I still hadn't really decided I wanted to be a chemistry major. I just was sort of science curious and chemistry curious. And so I took I sort of passed out of the introductory chemistry. And so I was able to take organic chemistry as a freshman, which is kind of unusual in the States, in a smaller class with a really inspiring professor. And again, that sort of got me more interested in the field. And then my TA from that class, ended up recruiting me into a lab. So it was small steps. It wasn't like I had some big epiphany at any point, really. It was sort of every step kind of led me along the path to end up where I am now.
One thing that we've mentioned before in chemistry world is you were given an award in high school recognizing your scientific ability. How important do you think it is to recognize that sort of thing when people are still very young, still making these decisions? How much impact do you think it had on you, knowing that other people could see the potential in you as well as your own interests?
Yeah, so my high school had this thing called book awards, and so like the top 20 students, the sort of teachers at the high school would sort of assign them a different book award, and so and the book awards were for sort of skills in some certain area, and so the book award that they gave to me was this Rensselaer Polytechnic award for achievements in mathematics and science, and I think that as a student at the time, I would not have chosen myself for that award. That wouldn't have been what I would have thought they would give me an award for, right? And so I think that it just sort of made me rethink what I could do, what the possibilities were. Even though I had taken this chemistry class and I'd done well in it, I wouldn't have considered myself a STEM person. But they gave me that award, and I think that sometimes just having someone recognize you for something, it can be an award, it can be just sort of answering your question or giving you some sort of affirmation, makes you think about yourself and what you could possibly do in a different way, right? So those little things. It's something I try to keep in mind when I interact with students, all the time, is just sort of that, it doesn't take much to nudge somebody, in a direction, or to frankly push them away by being sort of excluding them from something or kind of giving them negative feedback. So it just makes you realize how authority figures can really impact the direction that you end up going with your life,
Back then, if somebody had asked you to describe a chemist, or to draw what a chemist looks like, what would you have drawn? Would it have looked like you?
For sure, no. It's a good question. I haven't really thought about that. I guess, I think that, certainly, I think that sort of the stereotype, back then, and maybe still now for the sort of general public, would be sort of an older white guy in a lab by himself. This idea that you would go and you would work in a lab and you would toil away and have bubbling potions and things like that, and then I don't know, I guess would deliver some discovery at the end of the day. I think one of the great things about getting involved in research in college was seeing not just the science, which was obviously cool, but the sort of collaborative and international and just sort of the diversity of people that were in the labs, and that it was not like a solo enterprise, and that it actually, part of the fun was working with other people and interacting with other people, and that the community, the community of chemists was really strong and really exciting and really vibrant. So I think that was not at all what I would have thought when I was a kid. And I think that's something that I want people to see because it's an incredibly important part of the sort of enterprise.
Now, presumably you must have expected that you would find that community in gymnastics. We know that you were part of a team there that represented your college. So the chemistry may have come as a surprise, but how did the two sort of play together when you as you said, you chose your university for the gymnastics, not necessarily for the chemistry. Yeah. What did you learn from being a gymnast, representing, clearly working incredibly hard? It's not an easy feat by any stretch of the imagination to represent your college in gymnastics. How did that feel, and what did you learn from that to apply to the rest of your career?
Yeah, I mean, gymnastics is, I think all sports are, you have to work really hard. Gymnastics is one where, since probably third grade, I would have, come home from school, go to practice, for 4 or 5 hours, and then have to come home and do my homework at that point, and then get up the next morning and go to school, right? So it's just a sport that requires a lot of time from a very young age. And so I think that, number one, time management, which honestly, like when I'm trying to deal with things as a professor, when I was dealing with things as a graduate student, as an undergraduate, when I look at my, mentees now, being good at time management is one of the most important things to being able to be a successful scientist, because there's so much stuff going on, and figuring out how to manage it and move everything forward at the same time, incredibly important. So I think that's something that just sort of having to spend all that time doing gymnastics, every afternoon, every weekend, basically, we were traveling for competitions. So when I came into the lab in college, I would usually come in around 6 a.m. I would come in and do experiments in the morning before classes, so that I could do my classes and then go to practice in the afternoon. The second thing I would say is that athletics in general, gymnastics in particular, it's like this weird combination of like you're pursuing perfection, but you never get there. And there's an unbelievable number of failures along the way. Many of which you can't control, and some of them which you can control, and some of them which are in your head, and some of them which are, challenges, just physical challenges. And I think, I guess what I would say is that, as someone that was pretty successful in school, like I did not have as many academic challenges, right? Like, I knew if I worked hard in a class, I could get an A, right? In general, maybe other than physics, but that's a different story. But in gymnastics, it's like you could work really, really hard, and then, you would fail, and then you'd have to get up again. And I think that, one of the things that people that don't do chemistry don't appreciate is that it's not like just eureka moment after eureka moment, and you're just making these discoveries and everything happens in a really linear fashion. Like the challenge of research is that you have to deal with 90% of your experiments not working, right? And then, waiting for the, and sort of pushing forward even when things are failing and you're having all these setbacks and things like that. So I think that gymnastics, those lessons in gymnastics or other sports is just, it actually does set you up for success in science, because you're kind of accustomed to pushing forward, even though you're failing most of the time, I guess. So I think that, and I see that in students that have been successful athletes. Many of them do have that resilience in a way that students that have mainly focused on academics often are like, wait, my experiments aren't going to work every time. Like, when I take a class, I take a test and I get an A every time. And it's just difficult to change your mindset from that. So, yeah.
I guess in both athletics and science, analyzing, evaluating, understanding your failures is one of the best ways to progress, by knowing why this experiment didn't work or why you didn't quite get the points you expected in that particular move. Allows you to do better next time. And that's an important lesson to learn regardless of what field you're in.
Absolutely. Totally agree. Yep.
So in terms of the undergraduate research that you did, this seems to be a topic that at the time people were aware of, but wasn't really in the public mind at all, but now has come back to rear its head quite a lot. Because I understand that you worked, at least in part, on PFAS molecules, these what we're now terming forever chemicals that seem to be turning up almost literally everywhere we look. And we're starting now to get quite concerned about the impact that they have. Was this something you were aware of back then, or was it just another research project for an undergraduate degree?
So actually at the time, the interest, at least the motivation or the way that the projects were motivated was related to the sort of PFAS chemicals in the contributing to the ozone hole. So it was sort of the CFCs. So the concern wasn't so much, sort of fluorinated molecules in groundwater and things like that, but it was how they were going into the atmosphere and causing the ozone hole, above Australia and et cetera. And so, the motivation was sort of the same. It was to break these really strong carbon fluorine bonds, but of the sort of atmospheric pollutants, in order to sort of remediate them or to sort of break them down before they were released into the atmosphere, right? So these were things that were used in coolants, refrigerators and things like that. I think what happened was that they moved away from the really volatile derivatives that were released into the atmosphere to solve that problem. But then you ended up with more non-volatile derivatives that ended up in groundwater instead. So there was sort of, it was interesting that the problem has reemerged probably actually as a consequence of trying to prevent the sort of atmospheric release of those compounds. But that was the motivation. So it was actually kind of similar. The funny thing is that then a lot of my research is actually, because people, part of the reason people want compounds with fluorine in them is they have these really desirable properties, right? So part of the research that I actually do in my lab is actually figuring out how to make those kinds of bonds, right? And for some applications, you really do need to be able to do that in pharmaceuticals and, for example, positron emission tomography tracers. But then it cycles back to, okay, so we're making the bonds, but now we obviously want to be able to break them as well. So it's I don't know. Yeah, I feel like in some ways it's kind of full circle for that research.
Still on the topic of research, having done your undergrad and your master's, I think you had a couple of placements on the way, but I guess the real question is that your next big question in your life is what am I going to do a PhD? What am I going to do a PhD in, and where and who with? So talk us through that decision. How did you decide that this was your next step, and how did you choose a topic and a team to do it with?
Yeah, so I think this is kind of a long story, but what I was really interested in when I left, so I worked in Bob Crabtree's lab, and Bob Crabtree was known as a organometallic chemist, right? So working with transition metals and sort of the interaction of transition metals with organic molecules. And for me, that was really exciting because you sort of take organic chemistry and there's a lot of rules, and most of those rules are obeyed. But when you move to organometallic chemistry, the sort of rules and the mechanisms were kind of still, and I think still are being worked out, or they can be broken, or there's ways that, there's sort of, it kind of feels like you can do anything. And I thought that was really cool. And I wanted to understand that more. So I went to Caltech with the intention of doing organometallic chemistry, because actually when I was in Bob's lab, I didn't work on an organometallic project. So I got there, and there was a group, not the Grubbs group, that I wanted to join. That ultimately the group was full, and the faculty member wasn't able to take me. So I actually joined a bio-inorganic group to sort of do bio-inorganic chemistry, and I did that for almost a year and a half. And what I realized over that time, so I joined a different group. And I realized that just was not the really interesting science, I think, conceptually, but the doing it every day was not for me. So it was like I loved the project, but I didn't like actually doing the project, right? So I ended up wanting to go back to organometallic chemistry because that's what I really loved, and that's what I like doing every day. And had to kind of evaluate what group I wanted to join, and actually Bob Grubbs' group was not a choice that I had really considered, because I felt like his advising style was not going to be good for me. He was extremely hands-off, really didn't even, in many cases, give people a project. You kind of had to come up with a project yourself. And I just didn't think that would work for me. I felt like I needed a lot more supervision. But ultimately, that was the choice that I had. It was that or leave grad school. So I joined Bob's group, and it actually turned out to be one of the best decisions I ever made. So I switched groups about a year and a half into graduate school. And again, it was driven by this interest in organometallic chemistry. But I didn't think it was going to be a good choice for me in terms of just sort of, the sort of group, how he ran his group. But ultimately that freedom, it really pushed me, made me very uncomfortable, made me have to kind of find my way. And while it was not that pleasant, sometimes along the way, I think ultimately was what made me the scientist I am today. And I'm really grateful for that.
Worth noting that I think almost all of our audience, of course, will be familiar with Bob Grubbs. Even if they don't know him as an individual, they'll know his catalyst, of course. Yeah. And so the sorts of the people that you're working with already are clearly people who made significant waves in the chemistry community before you got to them. But that wasn't what drew you. You didn't want to work with this sort of big name in chemistry. That wasn't the appeal of it. You were more interested in solving that particular problem.
Yeah, I think that actually the big name in some ways was a sort of negative for me, because he was so busy, and so and just really, partially because he was busy and partially because it was just his style. He was just not a hands-on advisor, and I think for me, I felt like I really wanted to work with, I felt like I needed more guidance, right? And so even if the problems were interesting, like at least initially, I just didn't feel like I was going to be able to figure things out myself. And so I just was uncomfortable with that environment. But yeah, I think that I was forced to push myself out of my comfort zone in that regard. And actually, I think that it ended up being a wonderful and fantastic place for me to grow as a scientist. And I mean, Bob is just an unbelievable person and unbelievable scientist, and it just was such a role model for me to work with him. Yeah, he's amazing. So
it's fascinating to hear that you changed your mind, you changed your project after 18 months of a PhD. I think people very much have a perception that a PhD is a thing that you go into and 3 or 5 years later you come out of, and there's no changing once you're in there unless something very extreme happens. I mean, how would you advise people now? And presumably you get asked for this sort of advice quite often. If you have a master's student who's looking at going on into grad school to do a PhD, what's your advice to them?
Yeah, I mean, I think so. I don't know if I think this is probably not true in the UK and in Europe, but in the States at least, many and certainly Michigan was one of the leaders in this. Many universities now for PhDs have what are called rotations. So people will do a rotation in multiple groups before they make a decision. And I always talk to students about sort of the value of that vis-a-vis my experience, right? Because I think that there's two things that are important. Many projects can seem interesting conceptually, but doing them, which is what you're going to have to do for 5 years, it may or may not be interesting to you, right? So I think that the idea of like, you're going to have to do the science, not just think about it, is really important. And the second thing is that, and I think this is maybe even more important, is that you have to make sure that you get a good fit with your advisor, right? Because that's a person you're going to have a relationship with literally for your whole life, right? This isn't just a 5-year relationship. And even just for 5 years, you need to have it needs to be a good fit, how they advise, how they run their group, what their group is like, because ultimately, that's gonna be critical for your success and critical for having someone that's going to support you, going forward as well. So I think I'm always telling people, just because the person's famous, just because the science seems interesting, that might not be the best fit for you, and you have to make sure you get a good fit, because if you don't, it's going to be so much harder for you to be successful. So, yeah.
By the time you got to the end of your PhD project, do you think you had all of the skills you needed then? Were you confident at that point to say, yes, I am a researcher. I have the full breadth of skills that I need, and there's nothing else that needs to develop. I just need to research. You mentioned in a feature that we had in Chemistry World to Rebecca Traeger that actually it was doing your postdoc experience where you started to see more of the value of writing grant submissions and that side of science as well.
Yeah, I mean, I think there's a couple aspects of that. So I would say, did I have the skills to be a researcher? Yes. Did I have the confidence to be a researcher, independent researcher? Probably no. And did I have the skills needed to be a faculty member? Definitely not, right? Because the things they train you in grad school and even in postdoc are actually pretty orthogonal to the skills that you need to have as a faculty member. Like I would say one of the things that people don't realize is like how much time faculty members spend managing people, right? And that it's not just a question of sort of like, okay, I'm going to give you a project and help you manage that project, but sort of how do you get the best out of people, right? Like the best advisors are thinking all the time about what is the best project, what kind of training does this person need, what kind of skills, what areas do they need to grow in order to become the most successful researcher that they can be, right? And no one teaches you that, right? No one teaches you how to do that. And then I would say also, yeah, I mean, you can think about your individual project, but how do you write a bigger grant? How do you write how do you think about things beyond just an individual person's project to make a program? If you're gonna be a professor, you need to have a research program. It can't just be, a bunch of little individual projects. So how do you think about research on a kind of a programmatic level? And then, what is the best way to be the advisor that is going to help individual students and be able to push them and motivate them and give them feedback. And so I think like some of those things I learned as a postdoc, many of them I had to learn in on the job training, but certainly I think the value of the postdoc for me was seeing two different advisors that had really different ways that they sort of interacted with their students and thinking about like what works for me as a mentee, and then how would I want to run my group? And I think that was a really critical aspect of the postdoc and why I think postdocs are really important. Yeah. Even more than the science, right? Yeah.
That's usually a fork in the road for many researchers as well. You've done your PhD, you've done a postdoc or two. It's usually at this point that you have to start to make the decision between academia. Do I become faculty? Do I want to run my own lab? Or do I go into industry? Now, a lot of your work has been it's been sort of clear how it could be applied in industry. Yeah. Does that mean that there was a point where you were being courted by industry? Were people looking for people with your skills to go into industry jobs?
I mean, I would say so I got to the end of my postdoc, or the middle of my postdoc, when I needed to make a choice about jobs. And I mean, I had to make a decision about what kind of jobs I was going to apply for. So I wouldn't say that that I was getting recruited by industry, but I had to make a decision whether I wanted an academic job or whether I wanted an industrial job. And I think, I think I made the right decision, but also I think, I would say, for me, there was a lot of trepidation about the idea of running a lab and having to come up with my own ideas. And I'd had a lot of questions about whether I would be able to do that. But for me, the excitement of science is more like the discovery and the people, right? So discovering new things and then, training students and interacting with people. And so I think that industry, it just didn't have that much appeal to me because I felt like it was very directed at a goal as opposed to sort of exploration. So I think for me, like being told you need to pursue this drug or you need to pursue this product or you need to do chemistry towards this specific goal versus me being able to make the goals and me being able to decide that I think something is interesting and I want to study it because I think it's interesting. That's just how I work. And so I think it was a pretty clear choice in the end about which direction to go. Yeah.
So moving on to your lab, if we can sort of jump forward from postdoc to you running your own lab, how do you talked about have that sort of pulling together different projects into a model that actually makes sense and functions and everybody benefits. How do you draw that big picture and understand how to make separate projects from it? If you're keen to do that sort of grassroots exploration stuff, then potentially the trade-off there is that you could have people with projects that come to naught or end up not finding anything at all. How do you handle that?
Yeah, I mean, it's interesting. I mean, I think, so I guess what I would say is that I started out, with sort of things I was interested and then followed where the science went. Sometimes it didn't go in a linear fashion. It didn't go towards exactly the goal that we had at the beginning. But if there was something that I sort of felt was interesting, a student felt was interesting, we would kind of follow that line of reasoning, right? I think that being flexible is really important, right? If you have a goal, but something interesting happens along the way you can get success is not being so rigid that if you don't reach the very specific goal that you're going for, that you call it a failure, right? So I think defining success broadly, being flexible about directions, and being flexible. I mean, you bring in a team. They're going to bring in different perspectives, different interests, different things that they want to pursue. And so I think being open to, when students are like, I think this is an interesting result, talk about with them and let them sort of go in that direction. That can lead to really interesting things. But I would say that decision points on projects and deciding when to drop something and move on to something else, that is actually one of the hardest but also important things that you have to do as a faculty member, and I think especially in a project where you're like, I think this should work, I know we can figure this out. You get to a point with this, where you're working with a student who's in the lab working on something, and it's like you can just tell that they can't go on. They're like, I can't do this anymore. And so, having to be like, okay, even though I think this can work, we need to drop this. We need to move the student to something else so that they can have some success and move along in their PhD. So I'm not sure that totally answers your question, but it is like the infinite struggle of being a professor is figuring out how to balance those things and how to balance the direction that you think the research should go versus the direction that it ends up going because of what happens or what the students' interests are. And that balance is always sort of the ship that you're trying to steer, in whatever direction you're going. So
what is it you look for in a team member when you're choosing students for your lab? What is it that they do or say or what behaviors do they exhibit that makes you go, yes, I'd like you. You fit here in this team and I'd really like you?
Yeah, I mean, I think that, the students, I guess, I think when you start as a professor, right, you think, oh, I want the student with a very, very top grades or the very, very top scores or some sort of quantitative metric, right? Like that's what you think would be, you don't really know, I would say that, often, I mean, not always for sure, but often actually those are anti-correlated with success in graduate school. Because, like if you've had only success in your life, right, then getting in lab and having all these failures is, it just doesn't work so well, or you can get students that have been so successful in classes that they, it's like they want to just think to solve the problem as opposed to getting in the lab and doing. So I guess to me, I mean, not to say that, high scores and good grades are bad, but I guess to me, it's like, it's so much beyond that, right? It's sort of an attitude and enthusiasm for getting in the lab and trying things, sort of being adventurous, being willing to push yourself beyond your comfort zone. And then being, I think that, I'm often looking for students that sort of complement the skills and attributes in my team. So people that bring different things to the table, students, just as an example, I have some students that are really, really good at giving presentations. I have some students that are really, really good at writing. I have some students that are just really, really good in the lab. And then each of them needs to work on those other areas. And so having a team where they can draw on each other for the things that they need to work on and build, having students with different kind of career goals, right? People that want to go into industry, people that want to go into academia, people that are interested in the more mechanistic side of things or the more organometallic or the more organic, just having a team where everyone is not the same means that everyone can learn from each other more. When everyone is the same, you're not learning from one another because you all have the same skill set. And so I think, bringing people in that are enthusiastic, are excited to get in the lab and run experiments, and then bring different skill sets so they can all learn from each other is really valuable and important in a team.
You've said in the past that having a diverse set of backgrounds, you have international students, of course, as well as US students, having that diversity within your group is key, is part of what makes a group like this work. If I can get a little bit political for a minute, that feels like something that's a little under threat in the US at the moment. How are you feeling about that?
Yeah, I think it's scary. It's scary for me. It's scary for the students. That the idea that we would create an environment where everyone is welcomed and valued and encouraged and supported is something that would be viewed as anything but the most positive and important thing for a learning environment. You look at the words, diversity and equity and inclusion, and you think, how could those not be the centerpiece of how we want to train the next generation of scientists and then the next generation of leaders? So I don't see how you can create an environment where people will thrive and become the kind of scientists you want them to be, without creating an environment where everyone is welcomed and supported, and where people with different perspectives, people with different backgrounds, are able to join and thrive and be part of the group. So for me, I don't know, I feel like I learn more from my students in many ways than they learn from me, and having students from other countries, having students from different backgrounds, having students from different, disability status. And I every day as a mentor, I learn more about how to be a better mentor, how to be a better person from my students. And so I don't know, I can't imagine that not being like the central part of running a group.
It sounds like, and if you'll forgive me for harking back to earlier in the conversation, it sounds like you have a very different management and mentoring style to Bob Grubbs, who was very hands-off and allowed you to make your own decisions. How would you describe your style, and what influences do you think you've drawn from to come to that?
It's interesting, right? Because so Bob, I guess when I was in his group, I didn't think he thought about it in the slightest. I never thought that he thought about mentoring at all. I thought that he was just too busy, and that's why he was never, he wasn't that interactive. And I had this experience where, and so I was always angry when I was a graduate student, honestly, that everyone wasn't treated the same. I kind of had this kind of, oh, it's not fair. Why is this person getting this? And I'm not getting that opportunity and things like that. So I had this kind of constant complaints about this kind of thing. And there was one specific thing, I won't get into the details of it. But where I was very angry about something that happened, an opportunity that someone else had that I didn't get. So 10 years later, I went back to Caltech, and I was talking to Bob, and Bob was talking about the person that got that opportunity. And he was like, I'm so glad this person is doing so great now. And I feel like I gave them this opportunity, back 10 years ago. And that really changed their life and set them on a path for success in chemistry. And I was like, that is so interesting, because I was angry for 5 years about the fact that you didn't give me that opportunity. You gave them that opportunity instead. And Bob was like, what? He's like, why would I have given you that opportunity? You were doing great already. You didn't need that. I wanted you to be in the lab, like working on your projects. And so I think it was one of those sort of things where I didn't quite realize that he was actually thinking about these things all the time. And the way that he mentored people was deliberative and thoughtful. And so I think that impacted me a lot. But I think, the way that I think about mentoring is like, everybody needs something different. Everyone comes in with different skills. Everyone has different goals. And so for me, it's like about, for each individual person, the process of getting them from where they are to where they want to be at the end of their PhD, and helping them build the skills that they need and they want in order to get to the career that they want. And so I think that actually was what Bob was doing, maybe just a little bit less, actively, or maybe a little bit less, sort of clear to the people at the time. But I think, to me, it's like everyone is not the same, and everyone doesn't want to get to the same place. So you really can't give them exactly the same thing. That wouldn't be fair. That wouldn't be right. That wouldn't be a way to help everyone and get to where they need to be. So that's sort of how I think about it. Yeah.
I've just got one eye on the time, because I do want to make sure we still have lots of opportunity for audience questions. And there are great questions coming in. Do please keep them coming in. We will get through as many as we can. But I'm keen to talk about we talked earlier about recognition at an early age, being given the book prize that helps you to perhaps see yourself in a slightly different light. You are presumably now preparing to give your keynote speech as the 2024 recipient of the Janssen Prize. That's been going for 30 years. You're the first woman to win the Janssen Prize. How does it feel now to get an award, especially one like that where you're breaking a perceived glass ceiling, compared to back in high school when you got that book prize?
Yeah, that's an interesting comparison. I mean, I think so. Certainly, you look at that prize; it's amazing. There's many Nobel Prize winners on the list of people that have won that award. Incredible award. Certainly, just an incredible honor to win it. I think it is definitely true that in some ways that first award was more impactful in the sense that it really set me on my path. Whereas now, it is not going to change my everyday life in the same way, if I'm being honest, but I think, yeah, certainly it's an amazing recognition. And I think back to when I started and how few women there were in the field, especially in organic chemistry back then. And then I think to like 2 weeks ago, we had a incoming graduate student recruitment, and we had a table of organic students, and all of them were women. Not because we had any kind of, affirmative action or anything like that, because the best students in our pool, were women, and we admitted them, right? So I think that it's like amazing how the field has changed since then, where it just didn't even feel unusual to have an entire table of women, as 10 women, as our prospective student pool for that weekend. So I think that's awesome, and I think that like the hope is that 10 years from now it's not going to be unusual to have a woman win a prize like this, and that it's that we're moving hopefully towards a point where the field is recognizing the talent of everyone and include, just moving away from the idea that it's only sort of, white men that are able to be successful, have the skill set to be successful in chemistry.
It sounds like it really threw some contrast on what you see day to day working in a diverse lab with these tables full of very interested, engaged women who were at the top of their game, to then get a prize and be the only woman ever to have received it. That must seem a little bit incongruous.
I mean, it does. I think that's right. I mean, I think that, but I also think it's true that, like maybe the environment in my lab and the environment in our department is not representative of what it's like everywhere. But I hope that we're moving slowly asymptoting to that everywhere. Because it just makes sense, and it just makes sense.
I think I'll have one more question, and then we'll go to the audience for their questions as well. This is a biggie, and you can be as broad as you like. What are the future challenges that you want to solve, and what are the big challenges that you think chemistry needs to solve, let's say in the next decade?
That's a big question.
It is.
I think that, some things that, I have some sort of specific things that I'm interested in. I think, one of the things that I'm really excited about, I sort of started my career as an organometallic chemist. And I think that, most of the work that I've done has focused on sort of precious metals, on palladium. And I think that thinking about how to get non-precious metals to show reactivity that's like palladium, I would say, I guess maybe what I would say is this: what drew me into organometallic chemistry to begin with was the idea that metals can do like amazing things, right? And that if you put the right ligands on your metal, it will do things that are unexpected, that people said, well, this could never happen. And so I think, to me, thinking about these much more earth abundant metals and how you can get them to do the kind of things that you do with precious metals. And this could be for applications in catalysis. This could be for applications in, using them for, making medical imaging agents. This could be using them for applications in, for example, energy storage. But I think, really being able to understand deeply, how to do that, I think is an exciting area. I think that this sort of intersection, I guess that maybe the motivation behind why some people are thinking that they can just defund science is because they think AI is going to take over everything and going to replace scientists. I don't think that that's the case, but I think that the sort of interaction between sort of, machine learning and AI and chemistry and how we can use that in in a productive fashion to make things faster, to make things more efficient, to get rid of maybe some of the sort of menial tasks, or to make, to take the knowledge that we have and the data that we have and understand it better. I think that there are really exciting possibilities there for all kinds of implications, including, energy storage, catalysis, sort of all kinds of applications like that. So I think there's really exciting things to do there, and important problems to solve, or that can be solved that way.
It does seem that it's going to be an extremely valuable tool in the future, but right now it still needs a bit of refining before it becomes exactly AI, and machine learning becomes exactly the tool that chemists need.
Yeah, and I think I would just say also, like, people said, like, oh, high throughput chemistry or combinatorial chemistry is going to solve every problem that we have, and we're not going to need synthetic chemists anymore because we're just going to be able to do everything in high throughput. And that didn't happen, but it is a valuable tool that supports the things that actually, like, real chemists do. So I think that it's going to end up like that. It's not going to solve everything, but it is going to make our lives easier, and it's going to give us different tasks to do and different things to think about. So yeah, anyway.
Thank you so much. I'm going to get to audience questions, although I'm going to start with something that isn't actually a question. It's a comment from Pete, who said, "Nice orchids behind you." Now, do my eyes deceive me, or are those in fact Lego orchids that you have?
They are Lego orchids, yeah. I had, like, I'm into plants. I got really into succulents, but then my office doesn't have, like, amazing light, so I sort of, and I like to be in a cheerful office with, like, flowers and plants and things like that. So I have, like, a combination of succulents and also Lego succulents and orchids and things like that. So yeah.
I have a vase of Lego flowers in a corner of my house that doesn't get enough light to keep a plant alive. So I understand where you're coming from. Here we go. Let's dive into. Rita said, "Please guide us on how to choose a proper university." Now, your choice was driven by your interest in athletics, but if you were recommending a high school student now, what would you suggest?
I think that one of the things that you realize as a chemistry, for a university, as a faculty member, at least in the States, I know universities are very different in different countries, but I would say that here, you can get an amazing education almost anywhere, and so I think that in fact I know that this sounds kind of weird coming from someone that did go to these sort of, like, elite universities or whatever, but I don't think you need that to be successful. And in fact, the vast majority of our successful graduate students went to either very small colleges or state universities of various kinds. I think that for a university, thinking about like, are there opportunities to do research? Are there opportunities to, to interact with faculty? What level of interaction with faculty do you want to have? And what size of classes do you want to have are good things to think about. And then when you're going to graduate school, so choosing a graduate school, really thinking about the faculty members and the research matches, and not the ranking, right? Like, the ranking I don't think is helpful at all, because if you go to a school that's highly ranked and there's no faculty that you want to work with or that you think are a good match, it doesn't really matter. It's like, well, you're going to a university with a high rank and then you're not doing something you're interested in. So I think, to me, those are key things to consider for undergraduate and then for a PhD. And yeah, I guess in the UK it's different because you would pick your advisor when you pick the school, but in the States it's not like that. So yeah.
Question from NU, who says, how do you manage your time at the present? So you need time for teaching, mentoring, advising, writing articles, publication, still having time for your family life as well. You've already mentioned your son as well, who clearly you enjoy spending time with and advising on academic decisions. How do you manage your time at the moment, and what skills have you learned, or tips and tricks you've learned for time management?
Yeah, I mean, I would say this is like, you think you're really busy at every stage of your career, and then you move on in stage in your career and you get even busier. So yeah, I mean, I would say not as well as I could. But I think that one of the things that you have to accept when you're a faculty member at this level is you're never gonna be able to do anything as well as you want to do it, right? Like, if I did my teaching as well as I wanted to do it, it would take all my time. If I if I did, if I did my service as well as I wanted to do it, it would take all my time. So it's like you have to pick the things that you care about the most. Like for me, papers, things that are going to be disseminated into the public, it has to be right. So I gotta devote my time to that, even if it means I can't do as much of my teaching as I would really like to for it to be perfect, right? I would say so. It's sort of balancing and figuring out like how much is enough, and becoming comfortable with the idea that sometimes you're just not going to be able to do as a good job as you want to on some things, and you have to accept that and move on with them and not be a perfectionist about everything. So it's sort of a time management, and it's also sort of it's like a mental game to figure out, how can you, where are the places where it's just you're going to have to accept that it's okay to cut corners in order to be able to get everything done that you have to get done.
There is the saying, don't let perfect be the enemy of good. And it sounds like that's something you've taken to heart there.
Exactly.
A question from Joram, who says, what are important, I guess this is on similar lines, what are important daily habits and skills that might transform your average person into a good chemistry researcher or a good chemist?
The great question. I think, so for me, thinking about I think first of all, in terms of being a chemistry researcher, being willing to get in the lab and run reactions, like if you're an organic chemist at least. So doing experiments, right? Not just, I mean, thinking about experiments is great, and you definitely want to think and read, but I think, just getting in the habit of doing experiments every day, forcing yourself to think about new experiments, and because that's where discoveries come from, right? You can think and think and think and think, but if you're not in the lab doing things, you're not going to discover new things. I think being open to the possibility that your interpretation is wrong is unbelievably important, right? You have to think about being wrong as well as being right? Like you get a result, you get an NMR spectrum, you don't want to just accept that it's the product you thought it was. What else could it be? Am I sure this is right? Does this make sense? And I think not getting set on a specific result, like this reaction is going to give this result, but sort of thinking about it in terms of what actually did happen, because that can, imagine you're going for one product, but then you get a different product. But then maybe that's interesting as well, right? So I think that, getting in the mindset of like, this is what I'm trying to do, and if I don't do this, it's a failure. But more like, okay, this is what I'm trying to do. What happened, and why did it happen, and how can that inform the next thing that I do? So I think it's like a lot of it is mindset, running reactions, and thinking about what happened as opposed to the result that you wanted at the end of the day.
Super. I think I'm terribly sorry, but I think we have run out of time. Thank you so much for joining us. Thank you for spending an entire hour with us and our audience. Great questions. I'm sorry to those of you whose questions we didn't quite get a chance to get through. So many really good questions coming in. But thank you, Melanie. It's been really lovely to spend an hour with you. And I hope that we'll be able to do this again in maybe a few years' time, find out how things have changed. Maybe there'll be yet another award for us to talk about and talk about what that means as well. But thank you very, very much. We really appreciate it. We know you're busy, so being able to manage your time in such a way as to give us an entire hour is really, really appreciated. And I should also say a big thank you to the Chemistry World team, Chris Pink, Ada McVean, and Natalie Starkey, who initially set this webinar up before leaving Chemistry World for pastures new. And I should also thank Rebecca Traeger, who Melanie spoke to some time ago. She's Chemistry World's US correspondent, and she wrote an excellent feature profiling Melanie's life and work, which served for me as a great primer for this conversation. A lot of the facts I picked up from that. But one final thank you ever so much to Melanie. Thank you to all of you, the audience, for joining us. And we'll see you again for another Chemistry World webinar very soon. Thanks again.
Thanks.